Today I'd like to go over two types of problems. One involves strings and string tension, and we have a system in static equilibrium. And then the second one involves a ramp, and we're going to see if the object on the ramp is going to accelerate downward, and if so, by how much pushing force up would we need to counteract that. Okay, so this first problem I got from a classic text written by F.W. Sears, who was an MIT professor, and he wrote this in 1944. And this one involves a 200-pound weight hanging by strings or cords with these particular angles. Okay, and so we have, and it's symmetrical, so we can just treat one side as the same as the other. Okay, we have string A, string B, string C, and then they're identical, A and C on the other side. Okay, so we have a 200-pound weight suspended by these strings, and the question is, calculate the tension forces in strings A, B, and C. Well, as you might suspect, we're going to use free body diagrams for this. Okay, but it looks kind of complicated at first here, doesn't it? Because we have this string B connecting the two sides, and we have more than just a couple of we have 37-degree angle here, we have 53-degree angle here. So what do? Well, we're not just going to be able to draw one force diagram and solve the problem. It looks like we're going to have to maybe approach it by drawing more than one. So my first point object, I'm going to put it right here. Okay, that's going to be point object number 1, right where string C merges with the 200-pound weight. Okay, so let me draw a force diagram for that one. Okay, so I have there's my point object number 1 that I just outlined up there, and we have our 200-pound weight. I'll draw that force and label it. Okay, and then we have force C, the tension force C, pulling up at this angle here. Okay, and then the other string, also with tension force C, is pulling upward like that, symmetrically speaking. Okay, now I'm going to put everything in terms of the x-axis here just to make it convenient for me. This angle right here, what would it be? Well, that was 53 degrees there, so according to alternate interior angles, this one would also be 53 degrees, and the same with this here. Okay, so these are my two string tensions, C and C. They're equal in magnitude. They have the same angles, but just going off in different directions. Okay, so we have 3 force vectors in this free body diagram. 2 labeled C for string tension C, and then 1 200-pound weight pointing downward. Let's draw some components. That's always a good thing. Okay, components I'll just put in red. Those aren't vectors though, are they? So this would be C sine 53 here, C cosine 53. Okay. Alright. So now what? Well, and the same thing with this side. Okay, it would be C cosine, 53 here, and C sine 53 there. This pesky ceiling lights just went out again. Okay, so much for modern technology, automatic light shutoffs. Okay, so anyway, we have that, and that's our force diagram number 1. And since this object is in static equilibrium, we can say that the up components add up together to equal that 200 downward force, and then the left component is going to be equal and opposite to the right component. Alright, so let's take the sum of the forces in the x direction as a summation sign. That's going to have to add up to 0 if it's to be in equilibrium without any acceleration. Okay, and we have c cosine 53 going to the right, plus a negative or minus c cosine 53 going to the left, opposite direction, so they have opposite sign. They're going to add up to 0. Basically, if we just add c cosine 53 to both sides, we get c cosine 53 equals c cosine 53, which, you know, doesn't help us too much, does it? We already knew that from symmetry. That's okay. It was a good exercise. Now let's take a look at the y direction. Let's look at the sum of the forces in the y direction. They also have to be equal to 0. Okay? So, what are our up components? C sine 53. And we have 2 of those, that added together. So I can say c sine 53 plus another c sine 53 minus the downward force of 200 pounds add up to 0. Okay? Now we have 2 sine 53s. That's the same thing as 2 times c sine 53, and that's equal to 200. C sine 53 is equal to 200 divided by 2, or 100. Okay? And if we just keep on going, that'd be equal to 100 over sine 53, which is equal to 125.2 pounds. Okay, so just using our force diagram number 1, we were able to get the fact that tension C has a magnitude of 125.2 pounds. Okay, good. But we still don't know what the tension is in string B or in strings A. And so we need to get that. So what we can do is focus our attention at another intersection point right here. And this one is the same as this one. So all we have to do is one of them because they're symmetrical. We can use this as our second knot and draw a second force diagram. I'll put that up here. So force diagram, or free body diagram number 2, we'll put up here, and I'll draw the point object number 2 right here. And what do we have? We have tension force A pulling up at this angle with a certain amount of force. Okay, I'll label that tension force A, or just A for short. We also have string tension B. I'm not going to draw out the string length. This is tension now. It's going at the same angle as the string, but tension isn't the same as string length, is it? Okay, so I really should maybe put TA and TB here, just so you don't get misled into thinking that those are the lengths of the string. We also have tension C, which we found to be 125.2 pounds. We could just substitute that in right now if we want, the magnitude of that. So tension C, at this point, string C is pulling downward on knot 2, isn't it? Okay, so that's 125.2. That's string C. Okay, so C is equal, might as well just put that in there, 125.2 pounds. Okay, good. So now we have a force diagram which will help us solve for tensions A and B. Okay. Well, looks like a couple of these are going off at angles, so I'll split this one up into components and figure out what this angle is. Now we see from the original diagram that this angle here is 37, so that must mean that this angle here, alternate interior angles, must also be 37 degrees. So I'll write that down. And what else? Well, we have tension C. Can maybe use this, find this angle here. This angle here happens to be 37 degrees. That was 53. This one, therefore, if this is 53 degrees here, and this is 53 degrees here, then the complement of that would be 37. Okay. Or you could have put 53 down there. I just did 37. Okay. Well, this is C is 125.2, which we found out earlier, so I can just say, well, this is the opposite side of that, so that's 125.2 times the sine of 37 degrees. And I'll just simplify that real quick. So 37 sine, make sure I'm in degree mode, times 125.2. And so we get 75.3 for that component, magnitude of this. We also have this component here, and that would be 125.2 cosine 37 degrees, which is equal to, let's see, it's about 100. 99.99, so I'm just going to round that off to 100 pounds. Okay, so we have 100 pounds of magnitude there for that component, 75.3 pounds for the magnitude of that one. Okay, now we have these two components for tension A that we need to find also, but we don't know what that tension A is, so we'll just have to lay it out in terms of the variable TA. So this would be TA sine 37. By the way, a 3753 degree right triangle is a Pythagorean triangle with lengths of 3, 4, and 5. Okay, so anyway, 37 sine, that's 0.60. I'm just going to 0.6 TA. That just keeps it a little simpler for me. Okay, this would be TA cosine 37 degrees. Cosine of 37 is 0.8 approximately. So 0.8 TA. Alright, so now we're in pretty good shape. We can use our sum of the forces in the x direction equals 0, and the sum of the forces in the y direction, set that equal to 0 too. Okay, so in this case, what do we have for our x forces and components? We have tension B. Well, we have TA cosine 37 pointing to the right, so I'm going to make to the right positive. So TA cosine 37, oops, we already found that to be 0.8 TA. Okay, that's pointing to the right, so that's positive. And what are the negative forces or components acting on this point object? Okay, well, we have minus plus a negative TB, or minus TB. We also have this component here, 75.3, but it's pointing to the left, so it's a plus a negative. 75.3. Any other horizontal forces or components? Nope. So they all add up to 0. And if we want to make it plain and simple, we can just rearrange this. And so we get 0.8 TA. Now add these two negatives to both sides. Equals, well, let's see here. Equals TB plus 75.3. Okay. So that's what we have for that one. Alright, and that's about as far as we can get. We have two unknowns here, but we only have that one equation. Good thing we have another equation to fall back on. Sum of the forces in the y direction must also be equal to 0 if this is to be an equilibrium. Okay, well, let's look at the ups and downs. By the way, getting back to this, sum of the force in the x direction, 0.8 TA is to the right, so that'd be the right, equal T sub b and 75, those are pointing to the left. So the right equals the lefts. Okay, you always want to make sure the rights equal the lefts, and also the ups equal the downs, which we'll deal with over here. Okay, so now we get to the sum of the force in the y direction. What do we have? Okay, we have TA pointing up, to TA sine 37, excuse me, which is equal to 0.6 TA. So 0.6 T sub A, that's pointing up, so that's positive. And then we have one component pulling downward on that point object, and that would be 100 pounds. So plus a negative, or minus 100, equal 0. Ooh, that's easy. Okay, now add 100 to both sides. We get 0.6 TA, T sub A equals 100. Okay, so in other words, the up equals the down, and the left equals the right, so we're in good shape. Okay, let's solve for TA by dividing both sides by 0.6. So T sub A would be 100 over 0.6. Okay, 100 divided by 0.6, and we get about 167 pounds. So now we've found the magnitude of the tension force, TA. Found that force in this string. And it's also equal to the other side too, since we can use argument of symmetry for that. Okay, now that we know what TA is, we can substitute that right in to this equation here. Substitute that in for TA, and we can solve for TB. So I'll just go ahead and do that. 0.8 times TA, which is 167 pounds for TA. That's equal to TB plus 75.3. Okay, I'll clean that up a little bit. Okay. So this is equal to 133 1/3 about. That's equal to T sub B plus 75.3. I'll subtract 75.3 from both sides. And we get that TB is, the magnitude of TB is equal to 58 pounds approximately. Okay. Now your answers may be slightly different depending on how you round off, but this is the correct method. All right, so in summary then, the tension in string A is equal to 167 pounds. The tension in string B is equal to 58 pounds. And the tension in string C is equal to 125.2 pounds. Okay, I think I'm going to have to stop at this point, and we'll just call this part 1. Okay, I'll do part 2 for the ramp problem next. Thank you.